So we have another MATHCOUNTS problem. So this was a number 27 on the National Sprint Test. So what we are given is there is a equation y equals x plus 1 over x squared plus 1. And where we are told the x is real number. And we'd like to find the maximum and minimum value of the y values. Like this is a optimization problem where we usually have a couple tools for optimization. Like we just try like completing square, which usually helps, and maybe Algebraic inequality, even Cauchy. So we can just use those like tools. But in those cases, we really find either max or minimum value, not just both at the same time. So for that reason, it's not really helpful to use any of these like tools. Maybe we can just use another tool that we have, which is actually really powerful tool, which is we call discriminant. But there is no really obvious expression in the problem that we actually going to be using the discriminant. But let's really write the equation in a different way so we can kind of see the quadratic. Because only information we are told is x is a real number, which is kind of a hint that we might be using. So if I just do cross multiplication, so I'm going to get the yx squared plus y equals x plus 1. If I pull everything one side, so that will give us yx squared plus y minus x minus 1 equals 0. So to make it a bit obvious, I'm going to actually write the quadratic in a different color. Okay, so let's say this is x squared, and then we have like minus x, and I'm going to just write the other term. So I'm going to just write the quadratic in terms of x, and coefficient are going to be written as just in different colors. So think about this is a quadratic in terms of x, and the coefficient of the square term is y, and coefficient of the x term, because that's my linear term, is -1, and anything else has to be the constant term, which is y like -1, right? So this is my quadratic basically. So now we have this is a like quadratic in terms of x. And the reason I just like this because we are told x is a real number, which is actually telling us if x is a real number, this quadratic has a real solution. At least discriminant is 0. So then we can just go ahead and write discriminant. So just remember our like discriminant is like whenever you have ax squared plus bx plus c is 0. So we say the discriminant is like b squared minus 4ac, right? So then if I take the discriminant, in our case, our a is y, so then our b is -1. So if I just write the discriminant, so you should get -1 squared minus 4 times a, which is y, times c, which is y minus 1, is gonna be at least 0. So then if I clean this a bit, so you will get 1 minus 4y. If I multiply 4y by 1, so you will get minus 4y squared, and then this guy times -1 will be just plus 4y, and this is still larger than or equal to 0. So this is somehow promising. So if I clean this, but we don't really like the negative coefficient of the square term, so let's multiply it by -1, so that should give us 4y squared minus 4y and -1, but this is gonna swap the order. So then we got just this inequality. But you know, we can try finding the roots of this quadratic by using like completing square or quadratic formula. Even we try factoring, but it doesn't look like we can. So which is why I will just complete the square, because it is way better like than using the quadratic formula in most cases. So if I just complete the square, so this is gonna be like 4y squared. If I just remember my square of binomial is kind of way to go with the complete square in general. So a squared plus 2ab and plus b squared. So if I want to complete square, I like to kind of come this way. So, and then this is like a perfect square. So 2 times y to the second power. So then this is going to be 2y. And then this will be like the product of the 2y and 2, and another number should be -4a. That should be just -1. So that is why I will say 2y minus 1 to the second power. But when I expand this, I get this term, I get this term, plus another one, but this was like also -1. So in order for us to get this -1, so we should have -2, all of these. I hope that was clear. If that wasn't really like clear, so maybe review the complete square. And if I complete now the rest, just finding the y alone, so I can move everything on one side that has a square, so that should be 2y minus 1 squared is lesser than or equal to 2. So just remember, like if I have x squared less than like or equal to 4, there are like only the x value does work with the the square root of this number, which is 2, or larger than negative version of this one. So if you have this is like, I don't know, to make it general, so if I have x squared is lesser than a squared, then the solution of this guy would be anything lesser than or equal to a, but larger than or equal to negative a. So just remember that. So for that reason, we can have this guy as like 2y minus 1 has to be lesser than or equal to 2, but root 2, and larger than or equal to negative version of this guy. And just stress it, just simplification, just add 1 and divide by 2. So that will give us 1 minus root 2 over 2, lesser than or equal to y, and that's going to be 1 plus root 2 over 2. So like what we want was the minimum and maximum value of the y value, which is really nice because as you see, this is our minimum, this is our maximum. And if you add this guy to this guy, the roots will be gone. So you get 1 plus 1 over 2, which is just 1. And that is our final answer. So this was like number 27, as I mentioned, which really meant to be challenging. But as you see, the whole point is just using the discriminant in a way that we can get something out of it. And after that, we just use the complete square because that's really important tool for us to use, especially optimization problems, regardless of the type. And that was the approach that we just used. So here's my actually challenge for you to see if you can do this on your own. So this is another sprint number, I guess 28 on the national test, one of the old years. And try to see if you can really use one of these like tools to optimize your the expression, and I'll leave as a challenge for you. And then if you have answered, just comments below, okay? I'll see you in the next video.